Good evening, all. So, last class we have seen basics of the rotating machines like Fleming's left hand, right hand, how to apply, and also about simple loop generator. Simple loop generator. Okay. Now let's start the construction of DC machine. Next one is construction of DC machine. So unlike rotating machines of previous induction and synchronous, generally in induction machine and synchronous machine, we will see stator rotor part only. Stator and rotor. Yes, slip rings also rotating. Slip rings also rotating. Okay. Commutator also rotates. Slip rings also rotate. So when they are rotating, then they will, from the slip ring and brush, we are taking current or voltage outside to the load, rotating there. In DC machine, in the construction part, we don't see like separately stator rotor. Like induction machine and synchronous machine, we will see there only stator, only rotor. So other than that, we have some other parts like slip rings, brushes. We don't discuss there. Okay. In DC machine, we will see each and every part of DC machine separately. Let's see, like first we will see about stator frame. First, we will see about stator frame. This is also called in DC machine as yoke of DC machine. Yoke. After that, we see about field poles of DC machine. Field poles separately, because in induction machine particularly, you cannot see the poles. Induction machine poles are not visible to see, but they are present in the stator body and also rotor body, but you cannot see the poles. That construction we call homopolar construction. The poles are not visible to see directly there, but in DC machine you can see the poles. That is, in the stator, poles are projected outside, just like salient pole rotor. In alternator you have salient pole rotor, poles are projected outside, you can see the poles. And cylindrical rotor, you cannot see the poles, but salient pole you can see the poles. In the same way, in DC machine also the poles are visible to see. That is called heteropolar construction. The DC machine construction is heteropolar because here the poles are visible to see. That's why we call it is heteropolar construction. But induction machine particularly, it is homopolar construction. The poles you cannot see there, but there are poles. Stator also there is poles, rotor also there is poles. Okay. Next we will see about commutator. Commutator, and after that brushes and armature core. Fifth one is armature core, nothing but rotor only here. And the most important in DC machine is the sixth one, armature winding. Armature winding. See, if you ask what is important in this for DC machines for gate point of view, if you ask for gate point of view, I will say only this is important, armature winding, for gate point of view. But for engineering services, each and every part is important. So I don't say this is important for engineering service. But for gate, we can say by observation from previous years, 15, 20 years, this is the most important for gate. Sixth one. Okay. But for IES engineering services, all are important, but armature winding little more important among all of this. Okay. Let's see first one, stator frame or yoke. First one, stator frame or yoke. First, stator frame or yoke of DC machine. Let us consider this is the stator frame. let it is stator frame, and to the stator frame actually we connected poles. Field poles are connected to this. This is only yoke. Okay, this is only the yoke of DC machine, and additionally I'm drawing here poles of DC machine. The poles are projected outside. Okay, let it is one pole, it is another pole. Let it is north pole, south pole. Now observe, this is only yoke. Yoke is only this outer part. This is only the yoke. It is not completely yoke. This is second one, field pole, it is separate. But there is some purpose to draw these poles. This is first, let's see about what is the material the yoke is made up of. Stator frame or yoke of DC machine is made up of cast iron. Cast iron, CAST. Okay, not COST. Cast iron, also cast steel, but we don't use silicon steel here. Remember, in your total electrical machines, only different material is stator of DC machine. Stator of DC machine is made up of either cast iron or cast steel. These two we use. Cast iron for small DC machines, cast steel for large size DC machines we use. But we don't use silicon steel. If we use also, no problem. If you use silicon steel also, unlike other machines and transformers, no problem to you. But only problem is the cost will increase. The cost of DC machine will increase if it is made up of silicon steel, because cost is more, silicon steel cost. Then if we use, is there any advantage? Means no advantage. That's why no use of using silicon steel. Due to that reason, we use cast iron or cast steel. Cast iron or cast steel means the composition here is iron plus carbon only. Iron plus carbon, no silicon. Cast iron, cast steel, there is a slight difference in this composition. That is, in case of cast iron, the percentage of carbon is more than 2%. In case of cast steel, the percentage of carbon is less than 2%. Less percentage of carbon, nothing but cast steel. More percentage of carbon, nothing but cast iron. We call cast iron, that is. Almost same composition, little percentage change in the material will be there, that's it. But advantage of cast steel is, this cast steel will allow for any different shapes. Means if you want to design different shapes of the material, like stator, rotor, anything different shapes, then cast steel is supportable. Cast steel is best for molding. If you want to design some particular shape, cast steel is best. But when there is more percentage of carbon, it is very difficult for molding structures. If you want to design any shape, it is very difficult to you. That's why for all big size or large size DC machines, we prefer cast steel. Okay, so I will tell reason why we don't use silicon steel. First reason here. And one more is, the stator of DC machine is a solid core, very important. This is a solid core. We don't use laminations in this. We don't use laminations like other machines, synchronous machine, induction machine, and transformer. We don't laminate stator of DC machine. Not required to laminate. The main reason is, observe here. Whatever the poles are there, north to south flux will flow. North to south. And inside, south to north. This is the path of flux. North to south externally and south to north internally. This is the path of flux. Now, whatever the poles are there here, these poles are fixed poles or variable poles? Fixed. Always it is a north pole. Always it is a south pole. The poles will never change. So what is the flux direction also? Never change. Magnitude of flux constant, direction of flux also constant. So whenever flux is constant in any iron material, is there any eddy currents in that? No, the eddy currents are zero. No eddy currents. So when eddy currents will form in any core material, if the nature of flux in the core is alternating, then only eddy currents will come. Otherwise, no eddy currents, zero it is. So when there is no eddy current, no eddy current loss. If there is no eddy current loss, is it required to laminate the core? Tell me. Not required. Why should we laminate? Or if you want, you laminate. But problem of lamination is what? Cost increase, strength decrease. So if you get any question, this is one of the question in ISRO interview, that is, tell which machine is the strongest. Which machine is the strongest machine? DC machine, synchronous machine, induction machine. So that people don't know. Means that student don't know at that time. What is the strongest machine? DC machine is the strongest. Tell why DC machine is the strongest machine. Because of this reason only. The stator of DC machine is solid. Solid body it is. Very strong. But stator of synchronous machine, stator of induction machine is not strongest because they are laminated. When you laminate, strength of material decrease. But as it is a solid one, it is very strong. It is very strong. So, okay, the material we are adding anyhow silicon. So I'm not talking about material composition. I'm talking about solid and laminated here. So that is very common. Solid body is strong always compared to laminated body. So that's why the stator of DC machine is very, very strong when compared to other rotating machines. It is very strong because it is solid. Okay. Now, the stator of DC machine made up of cast iron, cast steel, and it is a solid core. No need to laminate. Since the nature of flux in stator of DC machine is DC or constant flux. Flux is DC or constant. Hence, there is no hysteresis loss. There is no eddy current loss. Then is it required silicon steel? Silicon steel we use for better performance, like low reluctance, high permeability, low iron loss and all. But is it required here? Not required. Then why should we use unnecessarily silicon steel to spend more cost on that? Cost increase. Then no one will prefer to buy that type of machine if it is made up of silicon steel. That's why normal cast iron or cast steel is enough. Okay. So this is about material. The yoke is made up of. Yes, flux is not alternating. Flux is DC, no, constant. Constant flux it is, DC flux, not alternating. In DC machine or synchronous machine, both flux is not alternating. The excitation or whatever the flux we are creating, the flux is not alternating. It is a constant flux. Okay. Next, purpose of yoke. See, what is the purpose of yoke here? Purpose. The main purpose is return path. Return path. Return path of flux. The yoke provides return path for flux. The yoke provides return path for flux. The yoke provides return path for flux. At the first point, it provides return path for flux. It provides return path for flux. Return path for flux. And one interesting thing is, see, the flux passing north to south is let total flux is 5. Total flux is 5 between north and south. Then what is the flux present in the yoke of machine? How much flux is there? At every point, if you see, how much flux will be there? 5 by 2 only, no? Half of the flux in this direction, half of the flux in this direction. 5 by 2, 5 by 2. Okay. So in the yoke of DC machine, only half of the flux will be there. If flux per pole is 5, or if total flux in the machine is 5, in the yoke always there is half of the flux. 5 by 2 only is present. 5 by 2. Okay. Next, second point is, see here. These field poles are attached to the yoke. This is yoke, only that outer surface is yoke. Now field poles we are attaching to the yoke or not? Yes. How we are attaching that? Can we attach with any glue or Fevikwik like that? Can we attach the poles? No, we cannot attach. So there is a arrangement called rivet arrangement like this, just like screws only. Rivets, we call it is rivets. The field poles are riveted. The field poles are riveted to the yoke. Means the yoke is providing a mechanical support to the poles or not? Yes. Suppose if there is no yoke, where you can place poles? Can you place the poles in the air? No. That's why the yoke is giving a mechanical support. The yoke is giving a mechanical support to the field poles. So they are connected to the yoke only always by rivet arrangement. Rivet is like a screw or a long screw will be there, bolts. So with that we will tight that field poles to the yoke. Okay, write that point. It provides a mechanical support to the field poles. A mechanical support to the field poles. So this is one purpose. It provides a mechanical support to the field poles. Next. Yes. Next, one more is, tell any other purpose of yoke here. Yoke. So yoke is protecting entire DC machine. That is common point for every rotating machine. Whatever the outside will be there, yoke or stator of DC machine, that must be very strong. That is like a protecting cover for every rotating machine. And one more important is regarding this yoke. In every rotating machine, stator is providing a mechanical support to the rotor also. So exactly here we have rotor. This is rotor. Now, how this rotor is present exactly uniform air gap exactly at the center of the stator? Who is giving support to rotor? Tell me. Who is giving support to the rotor? Stator only will give. Stator only will give. In every rotating machine, the rotor support is from stator body only through bearings. How it is like this. Let this is stator. This is common for every rotating machine. This structure is common. This is stator. This is stator. And this is rotor. So shaft is extended both the sides for large size motors. And who is giving support to rotor? The rotor support is from stator through bearings like this. Here we connect bearings. So like this support will be there to rotating body also from stator only. That's why stator should be very strong. These are bearings. So when we give supply to stator, the rotor starts rotating. If it is three-phase induction motor and all, it starts rotating. Now the bearings, whatever is there here, these bearings will provide a smooth rotation of rotor. The bearings will provide smooth rotation of the rotor. Okay, so who is giving support to rotor? Stator only through bearings. And this is called alignment of rotor. Alignment. So this is the job of mechanical engineers. If they don't align the rotor properly, so many problems will come in the operation of motors and generators. So what are the problems and all? In coming classes we will see. If rotor alignment is not proper, so many problems. So what are that? See, alignment means from this end to this end, let 2 centimeter gap, and exactly Here also same gap 2 centimeters should be there. Throughout the rotor, same gap should come 2 centimeters, for example. If it is not like it is 2 centimeter here and here 1.9 centimeter and here 2.1 centimeter, again 2 centimeter. If there is any small 1 variation also, it will affect your motor performance so much. So in what way it will affect, we will see again in the next classes. Okay, so write this point also in the purpose. Next point, it provides a mechanical support to the rotor and also commutator, because commutator is also on the same shaft. So that support is given by stator only. Okay, next, it protects the entire DC machine. It protects the entire DC machine. So this is the stator frame or yoke of DC machine. So make a note here. Note. See, stator of DC machine is what? Solid core it is, not laminated. Now in DC motors, we have one of the motor is DC series motor. Now a DC series motor, if you give AC supply to that, still it will work. What is universal motor? Tell me. What is universal motor? What is universal motor definition? Universal motor. AC and DC. That's right. So simply, the motor which works for both DC supply and AC supply, we call universal motor. The motor which works for both AC supply and DC supply, we call universal motor. Now, which motor like that? Series motor. Series motor, if you give DC supply or if you give AC supply, it will work normally. It will rotate normally. That is universal motor. Tell me examples where we are using universal motor, because many times in many PSU interviews, direct questions on universal motor. Asking that, can you give one example of universal motor practically? One example of universal motor. So there are many examples. Surrounding you only, there are many examples. Okay, see here. So most of you given answer mixers. Mixer. Okay, most of you given mixer. Okay, most of you given mixer. Yes, right only. But what is the problem is all of you saying mixer only. So why can't some other answer? Why can't some other answer? Okay, grinders. Okay. Okay. So what they will test in the interviews is the different one, different. You should be little different from others. That is the answer. See, in many places we use this universal motor. Mixers we use, and also in the drilling machines, we use a universal motor in drilling machines, and also in some toys also we use, and also in small table fans, in that also we use this series motors, and also in the construction side, for lifting applications, construction side we use series motor. Like construction side we use like hoist, DC series motor application only, like hoist or cranes. Here also we use, and also mostly all hand tools, whatever like drilling machines or cutting machines, whatever we have hand tool machines we call. Mostly in all hand tools, whatever carpenters, or plumbers or anywhere, whatever the work that is hand tools. In all these, we have universal motors only, hand tools, and also in trimmers. So these are all we are using. Many applications are there. And one more is in your motorcycle also there is universal motor. Can you tell where it is? In motorcycles also, in your scooters also, scooties. Where we have that universal motor? Tell me, in the motorcycles. Where we have that? Yes, very good. The answer is self-start motors. Now everyone is starting this, but you don't know which motor that is. Self-start motor. That is also universal motor. Self-start motor in bikes. Self-start. That is also universal motor. So many places we are using this, but we don't know proper idea of this motor first. So do you know in this also there is a commutator? See, then what is the difference between DC series motor and AC series motor? So our point is here, difference between DC series motor, AC series motor. Series motor, you can give DC supply, you can give AC supply, it works. But when you are giving AC supply, you need one care here. Tell what is that? Series motor only, but if you are giving AC supply to the series motor, one thing we have to change in our construction. What is that? Tell if you have any idea. No, commutator should be there. So don't think that we have to remove commutator. Commutator should be there. Tell me. Yes, very good. The answer is yoke. Yoke. That is, just now I said here, stator frame. What is the stator frame? Generally solid, because no need to laminate, because it is a constant flux or DC flux. But whenever you are giving AC supply, the stator frame of DC machine must be laminated, or the stator of series motor must be laminated. This is one of ESC question also. ESC question. So what is the difference between DC series motor and AC series motor? Constructional wise, 99% both are same. 99% both are same. You cannot identify also. This is DC series motor or AC series motor. Both are same except the stator. If it is AC supply you are giving to series motor, it must be laminated. Otherwise, your motor will burn definitely. Why? Because if it is solid core for AC supply, poles will interchange for every half cycle, north, south, north, south, north, south. Whenever the poles are interchanging, the flux also will interchange. Now there is hysteresis loss, there is eddy current loss. Then definitely your stator frame is overheated. It will damage the complete machine. That's why it must be laminated to reduce eddy current loss. So remember only this point right here. In case of universal motor, right, in this motor, the stator must be laminated. The stator must be laminated. To reduce eddy current loss. See, at the last of the DC machine, I will give about universal motor, how it is working, even if you give AC supply. Okay, to reduce eddy current loss. And whatever the students will get doubt, what is the need of commutator there if it is AC? So that is also I will show you with diagrams and all at the last. Okay, about this universal motor. So what happens if there is no commutator? Because people will get doubt generally. So when we give AC supply, then what is the need of commutator? Can we use slip rings in place of commutator? No. If we use slip rings, the motor will not rotate for AC supply. It won't rotate. So why it won't rotate everything, I will show you there at the last. Just remember this point meanwhile. If it is universal motor, the stator must be laminated. Remaining every construction part is same. Everything same. See, at least try to see one time the universal motor in your hand. Very easily available, na? It is easily available. In your home also easily available. So if you want to see, mostly mixers, every home will have mixer. So mixer means if any old one is there in your home which is not working, and you just keep it is aside, and for that type of motors, open the outer part of the complete mixer and try to take the motor outside, then at least observe there. So what is commutator, how brush is located with brush holders and all, you can see there directly. At least practically in your hand you can observe one time construction of DC machine. Okay, commutator will be there, definitely commutator must be there. This is the first one, stator frame or yoke of DC machine. Yes, in coolers also we have universal motors. No problem. That's why don't open whatever the mixers are working properly. Okay. No, no, no. See, stator means actually in every rotating machine, there will be one cover outside. Like, see this. If it is stator, no. If it is stator and if it is rotor, so above the stator, again, there will be one stator cover here. Again, on that, there will be one stator cover. One stator cover will be there, and on that stator cover some small holes also will be there at some places. Some holes will be there, and that holes we call vents, or simply we use that holes for better cooling of the stator bodies. In every rotating machine it will be there. Okay, but we are talking about only the outer stator part. Above stator, again one more layer will be there. Above the stator, one more layer. Yes, in series motor only stator must be laminated. Okay. So now second one is field poles. Right. Second one, field poles. Right. Field poles. Take the figure. So this is the side view of the field pole. So only one pole I taken, and every pole is having two parts again. One is pole core. Second is pole shoe. Every field pole is having two parts, pole core and pole shoe. And this part is called pole core. It is the upper part is called pole core, and this is pole shoe. This is pole shoe. Okay. Now on the pole core, we place field winding on this. There will be a field winding on this, like this. Field winding is placed because whatever the poles we are using in DC machine, they are electromagnets, but not permanent magnets. Electromagnets only we use. So as it is electromagnet, there must be some field winding, and it must be excited again with a DC voltage. Let it is excited, plus minus. Now current will flow in this direction. Based on the current direction, tell what is the pole it behaves. Apply right hand thumb rule. 4 fingers current direction, flux will be in the downward direction. Means this is flux direction, downward. Now flux is coming outside, means it is a north pole or south pole? Definitely north pole. Assume that it is the top one, and at the bottom we have one more pole here. So one more pole will be there like this. Okay, in this way, one more pole is there at the bottom, south. Now north to south flux and internally south to north through yoke. Okay, now let's see what is material. What is the material we use? Observe. Material, the field poles must be made up of silicon steel, no doubt in that, because electromagnets must be a good one. Silicon steel is best for creating good magnetic field. Silicon steel we have to use. Silicon steel. Okay, pole completely. Field pole is made up of silicon steel. And is it required to laminate? Generally not required, because flux is constant, no? So as flux is constant, actually you no need to laminate it is. But out of this pole core and pole shoe, one of the part of field pole we must laminate. So let's see which one must be laminated and why we laminate. Observe here. See this. There are open type of slots here. See, there are open slots. What are the slots we use in DC machine? Open. What are the slots in synchronous? Open. What are the slots in induction? Semi-open. These are all open slots. Okay, number of slots we have under the poles. Okay, number of slots. Now observe, whenever flux is coming from north pole, for example, flux is coming in this direction. Whenever flux is coming from north pole, flux always prefer to flow through low reluctance path. Now in the rotor we have slots. This is we call slot, and this is called tooth. Tooth of the rotor, slot of the rotor. This is slot again, this is tooth again. Slot, tooth, and so on. Now tell me, out of tooth and slot, which one will offer high reluctance? Slot will offer high reluctance and tooth will offer low reluctance. Slot will offer high reluctance because more gap is there here, and here less gap is there at the tooth. So tooth will offer low reluctance. Now flux always prefers to flow low reluctance path, that is tooths. Flux always prefer to flow through tooths only. Now whenever rotor is rotating, the flux line is trying to move towards tooth, always towards tooth. At that time the flux line will oscillate or not? Yes. Or if you see like this, this is rotor front cross section, and here we have pole. This is a pole. Let north pole it is, and there are number of slots in the rotor. Now whenever flux is going from this pole towards the north or towards the rotor, now it is fetching for low reluctance. Now observe, whenever flux is passing from north pole to rotor, now it is fetching for low reluctance. Now during that, the flux line will oscillate in this way. The flux lines will oscillate under the pole shoe here, one time towards tooth and towards tooth, towards tooth. Flux line is oscillating in this way. Now during that oscillation of flux, there is a flux changes or not? Suppose assume that now at one instant tooth is coming. Whenever there is a tooth, flux is little high. At the same position, slot will come. Then what is the same position flux? Reduce. Flux reduces, flux increases at one point. When there is a change in magnitude of flux, there is an EMF in that body or not? Yes, according to Faraday's law, whenever there is a change in flux, definitely some EMF will induce. Now, in the same way, under the pole shoe, this is our pole shoe. Okay, this is pole shoe. Now, in that under the pole shoe exactly, the flux lines are oscillating here, oscillating. So, due to that pulsation of flux, pulsation we call, the flux will pulsate under the pole shoe. Pulsation. Due to that pulsation of flux, there is a variation of magnitude. Due to that, some EMF will induce in the pole shoe, which causes some eddy currents. Now there is some eddy current loss in the pole shoe. Now this pole shoe must be laminated or not? Yes. That's why in the field pole, the pole shoe must be laminated to reduce eddy current loss. Because under the pole shoe, there is an experience of, it is experiencing oscillation of flux because of tooth slot variation whenever it is rotating. Due to that, the pole shoe must be laminated. Okay, the pole shoe must be laminated. But is it possible practically to laminate only pole shoe? No, because this is completely one part of the machine. Field pole it is. Pole core, pole shoe. Two parts it is having. So can you laminate only pole shoe like this? Only pole shoe. Can we laminate only pole shoe in this way? No, it is not possible. That's why if you see practically a DC machine, not only pole shoe, pole core also will laminate. Okay, like this. Pole core also laminated. Completely, pole core, pole shoe, both will be laminated. But if any question, if you get previously also in engineering services prelims, there is one question in DC machine, which of the following must be laminated? So in the option they given stator frame, pole core, pole shoe, armature core. So in that pole shoe is there. Pole shoe only you have to pick the answer, but not pole core, because according to this only the pulsation is taking place at pole shoe. Now there is some eddy currents in the pole shoe that is causing eddy current loss. So pole shoe must be laminated. But due to practical difficulty of laminating only pole shoe, we will laminate completely field poles. And attaching all the plates together, then it is becoming a perfect core, perfect pole, field poles. So practically we laminate both, but if you get any question in written test or anywhere question, your answer must be pole shoe only. Okay, remember this. Pole shoe must be laminated in DC machine to reduce eddy current loss. Now, what is the purpose of pole core? Purpose. Right, one by one. Purpose. First point. Pole core. What pole core is doing? On the pole core, we place field winding and excited by DC voltage. Excited by DC voltage. Right, that. The pole core provides. The pole core provides a place for field winding. A place for field winding which is excited by DC voltage. Which is excited by DC voltage to produce the required flux. To produce the required flux. The required flux. Okay, next. Second point. Now, what pole shoe is doing here? Pole shoe distributing the flux uniformly throughout the air gap or not? Yes. Pole shoe will distribute the flux uniformly throughout the air gap. Write that point. Pole shoe distributes. Pole shoe distributes the flux uniformly in the air gap. In the air gap. Okay, next. What is another purpose of pole shoe? Pole shoe. See, pole shoe is also providing a mechanical support to field winding or not? Yes. How it is providing mechanical support is, observe here. Now I will take two poles. Without pole shoe, with pole shoe. Suppose first I am taking without pole shoe. Without pole shoe. Let us consider it is without pole shoe. See, this is pole arc or pole face, but not extended outside. Now I will take with pole shoe, extended pole shoe. With pole shoe. This one. This is with pole shoe. Now, if you place a armature or rotor below this and also below this, let us place rotor below that. North pole, I am considering north pole. Now, let us place field winding on the poles, field winding. And here also I am placing field winding. Now, tell me out of these two poles, in which case the field winding is having well support, well mechanical support. Second one only here. Because in this case, the field winding is having a good base here because of elaborated pole shoe, extended pole shoe. The field winding may come up to this point, but not below that. But observe this one. So generally some vibrations will come in the rotating machines. Due to that vibration, there is a chance that the field winding may drop down because no support here and completely it comes outside because there is no mechanical support for field winding. But here the field winding will not come below this point. Up to here it may come, not below that because it is extended. So there is a mechanical support for field winding in case of pole shoe when compared to without pole shoe. Okay, write that point first. The pole shoe provides a mechanical support to the field winding The pole shoe provides a mechanical support to the field winding. Okay, next. There is another advantage of pole shoe. What it is? First, I want to give some important information. That is, see, assume that this is another pole, north and south. It is south. Now, let it is 0 degree and it is 180 degrees. Now, what is this angle we call 0 to 180? This is one pole pitch or not? 0 to 180 degrees. This is we call pole pitch. Pole pitch. What is pole pitch always? I think in synchronous machines you got this clearly. Pole pitch always 180 degrees electrically. Pole pitch definition is nothing but it is the angle between two identical points on adjacent poles. Two identical points on adjacent poles. So generally one pole pitch is 180 degrees electrical. Each pole will constitute 180 degrees electrically. So this is pole pitch. But if you observe, this is the pole arc. This is we call pole arc it is. Now this pole arc is covering how much angle with respect to the center position of the rotor? How much angle the pole arc is covering? Very, very small. Only this much angle. The pole arc is covering only a small angle, this much. When compared to pole pitch, pole arc is very, very small. But let us see the second case. This is the pole pitch. 0 degree, 180 degrees. And here this is the pole arc it is. So much arc is there. Pole arc is more. Pole arc is very high. Pole arc or pole face. Both are same. Sometimes we call pole face or pole arc it is. Now in this pole arc, how much angle it is covering? Observe with respect to center position of the rotor. So this much angle it is covering. Pole arc it is and pole pitch is this 180 degrees. Okay. Remember, always in DC machines, the pole arc to pole pitch ratio is not unity. Pole pitch is more 180 degrees. But what is the pole arc in both cases? First case, very less pole arc. Second case, little more pole arc. So generally this pole arc to pole pitch ratio will be 60 to 75 percentage. Remember this, 60 to 75. Pole arc will never cover 180 degrees. Pole arc will never cover 180 degrees in any machine. So approximately 60 to 75. Because in some of the numericals, you will see this ratio. Pole arc to pole pitch ratio in a DC machine is 0.6 or 0.7 or 0.75 like this. So whenever they given, you have to understand that the pole arc is covering 75% of pole pitch. Okay, remember this ratio. Remember this. Now let us see the flux distribution here. Shape of flux distribution. Flux. See, this is 0 degree, 180 degrees, and it is 90 degrees, center of the pole. 90 degrees. Now, in case of without pole shoe, only a small angle, the air gap is uniform or not. See here, from this point to this point, same gap it is almost. Then what is the magnitude of flux in this area? In the small angle, wherever pole arc is present, what is the magnitude of flux in that angle? Constant, because air gap is constant, reluctance constant, flux also constant. So if you draw approximately, you will get like this. Let it is 0 degree, 90 degrees, 180 degrees, and for another pole you will get this is 270, 360. It is 180 degrees. So this is the flux distribution in DC machine. What is the shape of the flux distribution? Flat top. The shape of flux distribution in DC machine is flat top or trapezoid. Flat top or trapezoid. This is without pole shoe case. Now let us consider with pole shoe case. Same shape you will get, but the magnitude of flux will increase. See here. Here, the angle of pole arc is very high. With respect to 90 degrees, let us take totally 70 degrees it is. And here only some 40 degrees or 50 degrees. So angle covers more. That's why for more angle, the magnitude of flux is constant. For more angle, the magnitude of flux is constant. This is the shape of flux for second one. It is also same flat top only or trapezoidal. So what is the advantage of second one? The resultant flux is very high. The resultant flux is more in case of pole shoe. But without pole shoe, what is the magnitude of flux in the machine? Less. Flux is reduced. But here flux is more because of pole shoe. That's why we always preferred pole shoe in DC machine. So there is one important relation. Tell me, in synchronous machines, what is the shape of main flux distribution? The shape of main flux distribution in synchronous generators is dash. What is the answer? The shape of main flux distribution. Yes. Answer is yes, sinusoidal. Very good. In case of synchronous machine, the shape of main flux is sinusoidal only. Sinusoidal required. Sinusoidal is must. But in DC machine, sinusoidal is not at all required. Not required. Sinusoidal not required. Why? Because what is the output of DC generator? DC voltage. So for DC voltage, you no need to bother about harmonics here. Harmonics we no need to consider. That's why harmonics topics we never discuss in DC machine. Not required also. Because output is DC. Even there is harmonics. See, if flux is flat top, what is EMF induced in the windings? Also flat top. Then what is the problem? No problem, because your output is DC voltage. You will get still if it is constant magnitude, no, that is advantage here, DC voltage. But in case of synchronous machines, the flux distribution must be sinusoidal. Okay. So for that reason, how we are getting sinusoidal flux in case of salient pole alternators, for example, how we are getting sinusoidal flux? By chamfering the poles like this. If it is a stator, if it is stator structure, and let us consider this is one pole, and we will chamfer that like this. At the center of the pole, gap is minimum, and towards this gap increase. So like that, if gap is increasing, what is the magnitude of flux towards the pole end here? Decreases. More flux here, then you will get a sinusoidal flux distribution. You will get sinusoidal flux distribution. Okay. So in case of synchronous, the shape of flux distribution should be sinusoidal. Then only EMF induced is sinusoidal. Still, if EMF is non-sinusoidal, how we are making that EMF sinusoidal? Tell me. How can we make EMF sinusoidal still? By using winding. What winding we are using? Short pitch winding and distributed winding. So using these two windings, if still there is any harmonics, we will eliminate that harmonics so that our EMF should become sinusoidal. So our main aim in synchronous generators is to bring the EMF in the alternator is sinusoidal, pure sinusoidal voltage. For that reason, short pitch winding, distributed winding. So in interviews also, question on short pitch and distributed is, which harmonics we are eliminating using short pitch winding? Tell me. Which harmonics we can eliminate using short pitch winding? Yes, everyone knows that. Fifth and seventh. Fifth and seventh we are eliminating using short pitch. And using distributed winding, we are eliminating third harmonic. Now third is eliminated, fifth is eliminated, seventh is eliminated. That is called dominant harmonics are eliminated using short pitch winding, distributed winding. If harmonics are eliminated, only fundamental is there. Then shape of fundamental is what? Sinusoidal. So EMF will become sinusoidal. Now here question is, why fifth and seventh is eliminated by short pitch winding? Why not third harmonic? And using distributed winding, why can't you eliminate fifth and seventh harmonics? Why only third harmonic? So this type of questions important. Remember it is. Because in short pitch winding, if you make alpha equal to 30 degrees, approximately short pitch angle alpha 30, both fifth and seventh harmonics almost eliminated. Because to eliminate fifth and seventh, the alpha required is nearly 30 degrees. That's why fifth and seventh only possible to eliminate. If you eliminate third, you can eliminate third, but fifth and seventh will not eliminate. Because for third harmonic, alpha required is 60 degrees, 180 by 3, 60 degrees required. If you put 60, these two will not eliminate. So as taking alpha 30 degree, as both fifth and seventh harmonics almost eliminated. This is only possible. Third harmonic you can eliminate, but if you eliminate third, remaining fifth and seventh will not eliminate. Okay, so that's why harmonics we talk only in synchronous machine, but not required for DC machines. Okay, that's why same as it is flat top flux. As it is we keep. Still no problem. So advantage of pole shoe is what? The shape of flux is flat top with more resultant magnitude of flux. More flux. If flux increases, EMF in generators increases. Okay. So write 1 point. Completed all of this. Triplet harmonics are absent default because of a delta connection or star connection. Automatically triplet harmonics will be eliminated. But still, if any small percentage of triplet is there, that is also eliminated by distributed viability. Okay. See, if air gap is more, along that point, flux is less. Because if air gap is more, reluctance is more, flux equal to mmf by reluctance. More reluctance, flux magnitude will reduce. So if air gap is less, flux will be more. If air gap is more, flux will be less. Okay, make a note here. Note. Make a note. See, what is pole pitch? Pole pitch is nothing but angle between two identical points. Suppose if you take a 4-pole case, North Pole, South Pole, North Pole, 4-pole case I'm taking, for example, South Pole. North, South, 4 poles I taken, and this is our rotor. Now, what is the pole pitch here? Same. The distance between two identical points. Suppose I'm taking the center of this pole. Okay. Adjacent to this, you take any other pole. Suppose south, this pole I'm taking, and take the center point of this pole also, and measure the angle between these two. This is called pole pitch. So, what is pole pitch? It is the angle between two identical points on adjacent poles. Angle or distance between two identical points on adjacent poles is called pole pitch. Like that, this is also a pole pitch, this is also a pole pitch, this is also a pole pitch. Total how many pole pitches are there? How many pole pitches? 4 pole pitches are there. So one pole pitch always 180 degrees electrically. Remember, one pole pitch is 180 degrees electrically, not mechanically. Mechanical angle is how much? 90 degrees only, no? But electrically it is 180 degrees we have to take. One pole pitch means 180 degrees electrical. Then total how many pole pitches are there? Total electrical angle is number of pole pitches. How many pole pitches? 4. Like that, if there are 4 poles, 4 pole pitches. If there are p poles, p pole pitches will be there. So total electrical angle is p into 180 degrees. One pole pitch is 180. 4 poles means 4 into 180. P poles means p into 180. Generally I'm writing. But what is the mechanical angle for every machine? 360 degrees. Now take the ratio of these two. Theta electrical divided by theta mechanical. This is 180 into P by 360. That is P by 2. So theta electrical is always P by 2 times of theta mechanical. Theta electrical angle is always P by 2 times of mechanical angle. Sachin Tiwari, as in transformer we studied, flat top flux causes peaky wave. See here, flat top flux means, okay, so you are considering hysteresis non-linearity, no? Is there hysteresis in DC machine first? Is there hysteresis loss? Okay, that's why we don't get that non-linearity concept in DC machine. That's why if flux is flat top, EMF also flat top. EMF will not be PQ. That is for only transformer due to magnetic material. Core is a ferromagnetic material having hysteresis loss. Based on the hysteresis non-linearity, we taken BH2. Okay. Yes. So for all our calculation, we have to take electrical angles only. Electrical angle, because mechanical angle anyhow fixed 360 degrees always. But electrical angle will change. Electrical angle is depends on poles in machine. Poles. That's why we always consider this equation in order to find total electrical angle. Okay. But not mechanical. Okay. Next. Remember this point. And another is, this is regarding in the note only, regarding types of slots. Types of slots. What are the slots we have totally? Three types mainly. One is open type of slot. Second, semi-open slot. And third, closed slot. Which slot we use in DC machine? Open. Not only DC, synchronous also we use open slot only. Semi-open we use only in induction machine. And where we use closed slot? Nowhere we use. Nowhere we use closed, because open slot means the slot is completely open. Semi-open means the slot is partially open like this. And closed slot means slot is completely closed, not at all open. Now, what is the purpose of slot first? To place winding in that. To place some winding. So when you can place winding easily in that? If it is open. If it is open, easily you can place. If it is semi-open, you can place but difficult. If it is closed, very, very difficult to place the windings. So I will show one example. See here. Assume that this is a rotor. Consider this is rotor. Now I will take one open slot first. Open slot I taken. Open slot. Slot is open completely. Now in this rotor, I need to place one coil. One coil I have to place. How to place that coil? How to place the coil in this? First, before placing the coil, I need a coil having 100 turns. I need to place a coil having 100 turns in that. So what I will do is, I will measure this distance first. I will measure this distance from this slot to this slot. Suppose it is 10 centimeters. I got 10 centimeters. And I will measure the length of the rotor also again. Length, side view. Length also I will measure. How much length it is. So length I got suppose some 30 centimeters. So height is 10 centimeter. The width of this rotor is 30 centimeter. Now I will put 10 centimeter. Some sticks, I will arrange sticks like this. 10 centimeter, 10 centimeter, and length is 30 centimeter, 30 centimeter. Now I will fix, this is with a rotor, like rotating body, like a handle here. Now I will make a coil on this by rotating that. I will make a coil. I will make a coil like this. 100 turns should be there in this. 100 times I will do this. Now it is a coil having 100 turns. So after making that, take the coil outside. Now place, this is one side. This is one side. This is another side. So I will place this side in this slot, and another side is another slot. And overhang you will get at the back side, overhang. Okay. So this is the placement of coil in the slot. Easily you can place because open slot. 100 turns coil also easily, not only 100, 200 turns also you can place easily. You can place easily in this slot because it is open slot. Now let us consider semi-open. If the slot is semi-open, can you place easily? Suppose slot is now semi-open like this. Can you place the same coil having 100 turns easily? No. Why? Because if you make a coil of 100 turns at a time, the size will be more. Each side is more thickness. Then that same side coil side you cannot insert here. It cannot insert because gap is very small. So you cannot place a coil at a time. 100 turns you cannot place. So what you have to do? Don't make 100 turns single coil. Now let us make 30 turns, 30 turns, 40 turns, and all in series only. 30 turns one coil, So keep aside, and again from the same end, again 30 turns, keep aside, and again 40 turns, keep aside. Totally one coil only it is. Now first place 30 turns coil, again insert 30 turns coil, again insert 40 turns coil. So like that we can place anyhow. Now let us consider closed slot. Slot is closed, not at all open. Now how can you place? If slot is closed, if you make a coil outside, you cannot place in that. You cannot place because there is no open to insert the coil side in that. You cannot place. So you should not make a coil outside. So if you want to place winding in the closed slot, you have to make a coil within the slots. Means, so insert the coil here, insert the wire here, one end, and from the back end of the same slot, insert again from back, and again collect from this. Now again insert here, again collect from here, again insert, again collect. Like that 100 times you have to make a, you need to, 100 times you need to place winding within the slots. 100 times you have to do that. Very, very difficult procedure. That's why closed slot we never use in the machines. But there are some advantage of closed slot. What is that? What is advantage of closed slot? Advantages? Induction is good. Mutual induction is better, but no use of that mainly. There is main drawback. And advantage of open slot is windings can be placed easily. Any bulk size at a time you can place. Windings procedure is very easy. And one more main advantage of open slot is leakage flux is less. Leakage flux is less in case of open slots. Leakage is less. Okay, so due to that reason, DC machine, synchronous machine, open only we preferred. Only in induction machine we use semi-open. The reason is it is working on the principle of induction itself. Induction between primary or stator and rotor, induction is good only when air gap is less. That's why only in induction machines the air gap is very, very less. The air gap is approximately 5 mm to 8 mm. Mostly in this range gap will be there. 8 mm means approximately take 1 centimeter. Induction motors will have very less gap, less than 1 centimeter gap between stator and rotor. And remaining DC machines and synchronous machine, you will have little more gap, greater than 1 centimeter in that range, 1.5 to 2.5. And synchronous motors or synchronous machines, among all the machines, will have very high gap, like 4 centimeter, 5 centimeter gap. More gap is in synchronous machine. Okay, so if you talk about air gaps, means induction machine is very less. After the DC machine, after that more gap in synchronous machines. Okay, so you will see why, what is the reason and all, you know already. Next, so remember these points. So which part of the field pole must be laminated? Pole shoe must be laminated to reduce eddy current loss. Remember this. And what is the shape of flux distribution in DC machine? Flat top. Shape of flux is flat top or trapezoidal. Next, third one, commutator. Commutator. Take the figure. So commutator vertical view, I'm drawing vertical view of commutator. So this is vertical view of commutator and it is having some number of segments. So these are all commutator segments. These are all commutator segments. Okay, and these are all mica insulations. These are mica insulation. So each segment is isolated by mica insulation. Each segment is isolated by mica insulation. These are the brushes on commutator surface and these brushes are held by brush holders. This is brush holder attached to stator body only. This is brush holder we call brush holder. And in that we have one spring. That spring will push the brush towards the commutator surface always. Okay. So there are number of segments. So first of all, the material the commutator is made up of material important that is hard drawn copper. The material is made up of hard drawn copper. Remember this name, hard drawn. Actually, previously we have seen last class in the simple loop generator. Current is flowing in the loop inside and current is coming outside to the load through commutator and only. Current coming outside through commutator and brushes. Okay. So as current is flowing through that, so as current is flowing through the commutator, actually it must be made up of copper. But it is not purely copper, it is having some impurity in this, like some composition added, like copper plus a small amount of iron is added to this. Copper plus small amount of iron. The reason is in order to withstand the mechanical stresses here. Why mechanical stresses? Whenever commutator is rotating, there is a friction between the commutator surface and brushes. There is a friction between commutator surface and brushes. To withstand that friction, it should be made up of hard drawn copper. If it is only copper material, no, at high temperature, commutator will burn because copper cannot withstand high temperatures. It will melt easily. That's why we add some impurity like iron material or carbon plus carbon also added to this little. Then the strength of the copper will increase. So that is called hard drawn copper here. To withstand the friction between the commutator surface and brushes. Okay. Now this is material. Now how many commutator segments will be there first? Number of commutator segments. Number of commutator segments. Remember this equation, it is always equal to number of coils in armature. Number of commutator segments is equal to number of coils. So in the armature winding, I will show you the complete diagram of armature winding. So there you will understand. Number of coils, if 12, 12 commutator segments required. If it is 24, 24 commutator segments required. Okay. And the mica insulation thickness is very small. It is 0.5 to 1 mm approximately. The mica insulation thickness is very small. 1 mm is only this point. This point is 1 mm. So that much small thickness will be there for mica insulation. Every segment is isolated by mica insulation completely. Okay. This segment, no conduction. They are separated by mica insulation. And internally, there are many coils connected to this. There are many coils here, like this. Okay. Now, purpose of commutator. Let's see what is the purpose of commutator. So before that, so one important information here is, this is also interview. Sometime they are asking, what is the reason for spark at brushes? What is the reason for spark at brushes? Tell me. Generally in DC machine, the main problem is spark. The main problem of DC machine is sparks. Because of that only, mostly the machines will damage. Because of the spark coming between commutator and brush. If you take induction motor, you don't have that brush assembly first. So in induction again, two types, squirrel cage, slip ring. In the slip ring, we have slip ring brush. But in case of squirrel cage, there is no slip ring, there is no brushes. That's why the most useful induction motor is squirrel cage induction motor only. The most using induction motor is squirrel cage induction motor. Slip ring rarely we use, particularly in traction now. At present situation in traction, what is the motor we are using? Tell me. So most of the people, when we ask what is the motor using in traction, is series motor. Series motor, it is an application you can use there in traction. But nowadays we are not using series motors. We are using three-phase induction motor only. And that too, which motor? That is squirrel cage induction motor or slip ring induction motor? That is a squirrel cage induction motor. Because squirrel cage induction motor is the best induction motor. Why? Because once you buy the motor, you no need to spend single rupee also on that for a long time. For a long time. The reason is there is no slip rings, there is no brushes, and in the squirrel cage rotor, whatever winding we have, copper bars, heavy copper bars, they never damage, they never burn. Even high current will come, the rotor winding will never damage. That is a permanent rotor almost. If anything is damaged in the rotor, which one will damage is that end rings will damage. End rings. Whenever end ring gets open, motor could not rotate. End ring only mostly will damage in squirrel cage induction motor. Okay, that's why mostly we are using squirrel cage induction motor only. Now, what is the reason for spark at brushes is, there are two reasons. One is constructional reason and other is operational reason. One is constructional reason and other is operational reason. See, there is no proof here. Number of commutator segments equal to number of coils. How it is means there is no proof right now. In armature winding, I will show you how many segments minimum required to connect the coils. So there you will get. That's it. Okay. Remember up to this. Now there are two reasons for spark. One reason is constructional problem. Constructional reason. And other reason is operation reason. Operational. Constructional reason means, observe here. There is a spring attached to the brush, just like it is tail it is. A spring will be there. So what is the job of spring here? Uh, Due to the friction, brush size will reduce. Whenever friction is taking place, as it is made up of graphite or carbon, size will reduce. Whenever size reduce, if there is no spring, suppose, then a gap will come between stator, that commutator surface, and brush. Gaps will come, open circuit. If it is not contact with commutator, your motor will not rotate. Same problems you will get in your mixers. I think most of you has taken your mixer to the service shop to change the brushes. Okay, so I think most of you changed in your home also. Brushes will damage mainly because of friction. Brushes size will reduce. Finally, total brush is worn out. So one problem is spring problem here. Suppose if spring is damaged inside, then who will push the brush towards commutator surface? No one can push. Then open circuit or loose contact will come. When there is loose contact, there is a heavy sparket brush. Heavy sparket brush. That is one reason. Problem due to construction or defect in the material. That is one reason. And another reason is operational. This is due to armature reaction. So we will see in the next coming classes. Armature reaction. So due to armature reaction, one of the effect is cross magnetizing effect. Due to that, mainly the problem in DC machine is spark. It will cause sparket brush. So how it is causing sparket brush, I will show you there in the cross magnetizing effect. So remember this. So these two are the reason for sparking at brush. Okay, let us consider there is a spark. So what is the problem of sparket brush? What happens? What happens? Total machine will burn. See how it is. Assume that these are the number of segments in the commutator, and on this commutator surface there is a brush. Assume that this is a brush. So whenever commutator is rotating, friction takes place between commutator surface and brush, which causes some spark at brushes, sparks. Now, if the spark is continuously coming, you did not reduce, you did not observe. If spark is continuously coming, first what happens is this mica insulation will burn, because spark means heat. Because of that, insulation will burn first. That is very thin insulation. Insulation burn. Like that, every insulation will burn. When all insulations are burned, total commutator segments act as a short circuit. Total commutator segments behaves as short circuit. Under that condition, your commutator looks like a ring fire. Your commutator looks like ring fire. So once there is a ring fire in DC machine, now you no need to think about DC machine. No need to think, just leave that, because complete DC machine damages. Completely, that is armature winding will burn, commutator burn, brushes burn. Only the stator rotor structure will be there. That's it. No winding, no commutator, no brushes. Completely it will melt. Copper, it will melt. Brushes will burn. Armature winding completely will burn because of this thing, ring fire. Because to the same commutator segments only we connected coils of armature. Armature coils are connected to this. When it is short circuited, armature coils also short circuited. Total winding will burn. That position of commutator we call ring fire. So what is ring fire? Just like in Diwali we use chakra, no? Chakri or chakra. Diwali we use chakri. Same as it is, however it rotates at high speed with fire, in the same way your commutator looks for some time. That means complete DC machine damage. So what we have to do to avoid ring fire? Spark we have to reduce first. Very, very dangerous thing it is. So to reduce the spark, what we can do? The spring, whatever we attach, that must be perfect. That must be perfect. And armature reaction also there, that we have to reduce. So that we will see methods. Okay, right. Purpose of commutator. Purpose. What is the purpose of commutator? Tell me. Already we have seen previously in simple loop generator. It converts AC into DC. For which case it is generator case. If it is a generator, AC induced converted into DC, that is. Suppose if it is motor, DC motor, what is the supply we have to give for DC motor? DC supply. But when you give DC supply, again inside the armature or loop, what is the nature of that EMF or current? AC only. If it is a motor, we give DC, again it is converted into AC by same commutator. So how it is means, you go to same simple loop generator again. There we have connected a resistive load. So you remove the resistive load. Remove the resistive load and place a DC supply there. That is only motor. Okay. So at the last, I will show you that figures again, how series motor, universal motor is working. At the last, I will show that figures. Okay. Right here, it converts the induced AC into DC in case of generator. In case of generator, hence it is called as rectifier. It is called as rectifier. So in generator, commutator is treated as rectifier. But if it is motor, DC is converted into AC. That is called what? Inverter. DC converted into AC means inverter action. Right. It converts the applied DC into AC in case of motor. In case of motor, hence it is called as inverter. It is called as inverter. So in case of generator, we call it is rectifier. In case of motor, we call it is inverter. So same commutator behaves as rectifier and also inverter. And is it controllable or uncontrollable? Uncontrollable only, because commutator is not controllable. Uncontrollable it is. How spring will work here? Spring. See, this is a brush holder. See, brush holder. I will take another diagram here. This is a brush attached to commutator surface, and this brush we place in a brush holder with a spring here. Okay. Now see, while placing the brush, see, initially the brush size is this much. This much is the brush size connected to the commutator. Now the spring size is very, very small here. Why very small is, we have pressed the complete spring, completely it is pressed. Then it is the size of the brush. But whenever it is working after some months or years, so years will not be there if it is regularly working now. Definitely within 1 or 2 months itself, the brush size will reduce to this much. Whenever size is reducing, what the spring is doing? Pushing that brush towards surface of commutator. Whenever it is exactly contact with commutator surface, spark will be less. Okay, the spring like that, it is pushing, it is pressing, the spring will open now. Whenever brush size is reduced, spring will open. That means spring is pushing the brush towards surface of commutator. Okay, clear now? So arc surface means this is stator. This is not arc surface, stator it is. Because brush holder is connected to stator surface only. Stator. That's why it is drawn like that. Okay. this is about commutator. So take a break. So after break, we see the remaining parts. Take a break. Why we convert DC into AC in motor? So we are not converting. So when we give DC to the commutator, that is in simple loop generator, I said remove the resistor and give DC supply. So when you give DC supply, again internally it is going to armature inside. Suppose you same figure you take and apply DC voltage, internally you will get AC only. So automatically when we give DC, it will become AC in the loop internally, AC alternating. That's why in more DC motors, when DC is applied, converted to AC it is. Commutator is converting. DC motor square wave. Which one that is? Ah, yes, like trapezoidal shape only, like a square approximately. Right. Next, the next one is, what is the fourth one is brushes. Fourth one, brushes. So where brushes are located? On the surface of commutator in brush holders. This is only. Brushes are located on the surface of commutator in brush holder. In the brush holder we place it. Okay, and this brush holder is attached to stator surface. Brush holder is attached to stator surface. That's why brush holder will never move, it is fixed. Brush also fixed in that. Now let's see about material first. The brushes should be made up of which material? The brushes should be made up of copper. The brushes should be made up of copper because current is flowing through that. But we don't prefer copper, we use carbon. But carbon brush is preferred. Carbon is preferred. Actually, it should made up of copper, but carbon is preferred. Why we preferred carbon? Due to some advantages. What are that advantages? Let's see. Carbon is preferred due to the following advantages. Due to the following advantages. Following advantages. What is one main advantage of carbon brush? The main advantage of carbon brush is, yes, right, that is self lubricant. If you observe here, whenever commutator is rotating, there is a friction between brush and commutator surface. Generally, how we reduce friction? By using some lubricant like oil, grease, like this. But can we use any oil or grease materials here? No. We should not use any oil or grease here at the brush position because there is a current flow in this. So as current is passing through the brush and then commutator, you observe the previous simple loop generator. Through commutator only brush and then it is entered into brush and then comes outside. So because of that reason, we should not use any lubricant. That's why if we use carbon material, the advantage of the carbon is it is a self lubricant. Means when there is a friction between commutator and brush, a fine powder from the carbon brush itself will release. Now that powder itself provide a smooth rotation. It will provide a smooth rotation here. That is as a lubricant. So no need to use any again specially lubricant in this. That itself will act as lubricant. Okay. There is no additional lubricant material required.
Sir,
Right.
nothing, sir.
Okay. Okay. Right. First point. It is a self lubricant material. It is a self lubricant material which reduce the friction between commutator and brushes, which reduce the friction between commutator and brushes. Okay, next, second. The other advantage of carbon brush is if you made the brushes with copper, because of friction, temperatures will come. At high temperature, copper can melt easily, but carbon will withstand at high temperatures. That's why we call carbon is having high thermal stability when compared to copper material. Okay, that is one advantage of carbon. It is having high thermal stability. It is having high thermal stability. Okay, it is having high thermal stability. Next, one more advantage is out of copper and carbon, which is having high resistance. Yes, no doubt. Definitely, carbon will have high resistance. Copper will have low resistance. Carbon is having high resistance. So that is also advantage here. How it is advantages? As it is having high resistance, it will improve commutation of DC machines. Commutation. So that is one separate topic, commutation. So that we will see in the later classes. So just right here. Due to its high resistance, it will improve commutation. It will improve commutation. It will improve commutation. So what is commutation, how it will improve and all, we will see later. Okay, in the commutation topic, we'll see there. So these are the advantages of carbon brush over copper brushes. Now there is a disadvantage or not? Yes. What is disadvantage of carbon brush? High resistance. That is itself disadvantage. When resistance is high, as current is passing through the brush, some voltage drop will take place. That voltage drop we call brush drop. Whatever voltage drop is taking place, that is we call brush drop only. That is very small. At the same time, some power loss also takes place due to brush. Some power loss also will take place due to brush. That is brush power loss. Generally, we neglect in our calculations and all, we don't consider brush power loss or brush drop. But if in any question, if you have the data of brush drop, you have to consider brush drop in the equation. Otherwise, neglect the brush drops. Okay. Due to high resistance, a small voltage drop will take place. A small voltage drop takes place. Called called brush drop. It is called brush drop. So this brush drop is approximately 0.5 to 2 volts per brush. So it is approximately 0.5 to 2 volts per brush based on the size of the brush. Very, very small drop called brush drop it is. Oh, wear and tear of carbon is less compared to copper. That is also advantage of carbon brush. Okay, next. So the only drawback of carbon brush is high resistance, some voltage drops. But compared to disadvantages, we have good advantage of carbon brush. That's why we use carbon brush. Not only carbon, we have another material, graphite. Graphite also we use for brushes, but graphite is preferred for large size DC machines. Where the friction is very high, there we use graphite material. Carbon, better than carbon, graphite is best for large size DC machines where friction is very high. Okay, graphite also we use. Next, purpose of brushes. What is the purpose of brush? Tell me. Purpose of brush. We are supplying current to the motor through brush. We are taking outside the current from brush in case of generator. If it is generator, we are collecting outside. If it is motor, we are supplying inside to the motor through brush only everything. Okay, write the 2 points. Purpose of brush. It is used to collect the current. It is used to collect the current from the armature in case of generator. In case of generator, if it is generator, we will collect the current outside. If it is motor, we will supply the current inside. Right, it is used to supply the current. It is used to supply the current to the armature in case of motor. Okay, so purpose of brush, just to collect and to supply. Without brush you cannot collect, you cannot supply. No generator, no motor will work without brush. If brush is damaged also, you cannot operate the motor or generator. Okay, next, right, fifth one, armature core. Armature core. Take the figure. So open slots. See, armature core must be laminated to reduce eddy current loss. So in total DC machine, two parts must be laminated. What are the two parts? Pole shoe and armature core. These two only we must laminate in case of DC machines. Remember that. These two must be laminated. So it is side view of the armature core and there are laminations, and considering this is the field poles, This is one pole. Let it is south pole. North, south. Now exactly in between the poles we have this armature core. Now armature core, why we are laminating is, from north to south there is a flux. Flux is passing from north pole to south pole. Through what it is passing? Through the armature core or not? Yes. The flux is passing from north to south through armature core only. Now whenever armature is rotating or rotor is rotating, it will cut that flux lines or not? Yes. Flux is stationary only, constant flux only. Even flux is constant, armature core is rotating, no? Armature core is rotating. So whenever armature core is rotating, it cuts the flux lines. Whenever it cuts the flux lines, an EMF will induce in the armature core. Now due to that EMF, if it is not laminated, there is a possibility of circulating currents. But as it is laminated, that eddy currents or circulating currents will reduce, then eddy current loss also reduce. So it must be laminated, and it is made up of silicon steel. It is made up of silicon steel to reduce eddy current loss. We use silicon steel and also laminations. So how to reduce eddy current loss? Suppose if you get question how to reduce eddy current loss, we can reduce eddy current loss by two methods. One is silicon steel, other is laminations. Don't say only laminations. Silicon steel, why we are adding silicon to the steel? Silicon steel is nothing but adding silicon to the steel material. What happens when silicon added? Conductivity of material reduce. Silicon is not good conductor. So when silicon added, sigma reduce, conductivity reduce. When conductivity reduce, magnitude of eddy current reduce. When current reduce, loss also reduces. That's why both we use silicon steel and laminations to reduce eddy current loss. So already we have seen in transformer. Okay. So it is made up of silicon steel and laminated. Now what is the purpose of armature core? Purpose. What we place in this? This armature core provides a place for armature winding. The armature winding we place in the slots. Armature winding we place. And where is the field winding? On the pole core. Field winding is on pole core. Armature winding is on this armature core or rotor. And another purpose of armature core is, observe this figure. This armature core is providing a low reluctance path to the main flux or not. See how flux is passing from north to south through armature core only. Suppose you remove that armature core. Remove armature core from this. Then completely air it is. Now air will offer high reluctance to the flux or not? Yes. But when there is armature core, the flux is passing from north to south through this armature core only. So now it is providing a low reluctance path. So these two are the purpose of armature core. First one is it provides a place for armature winding. It provides a place for armature winding. Okay, next. It provides a low reluctance path. A low reluctance path to the flux. A low reluctance path to the flux. Okay. So this is about the armature core made up of silicon steel and laminated it is. That is important. Silicon steel and laminated reduce eddy current loss. So totally in DC machine, which are laminated, pole shoe is laminated and armature core is laminated. These two are laminated. Remember that. Pole shoe and armature core must be laminated in DC machines. Yes, armature and rotor both are same. See, in synchronous generators, where is armature winding? Where is armature winding? Stator. And where is field winding? Rotor. In DC generator, where we are placing armature winding? Rotor, that is armature core. So here we are using rotor, and field winding we place on stator, opposite to synchronous. Because if you want DC, there must be a commutator. So when commutator will convert AC into DC? Whenever it is rotating. So when it will rotate, if you connect the commutator to the rotor, and armature or conductor also should rotate. Whenever armature winding is rotating, at the same time commutator also rotating, simple loop generator, then only you are getting DC. Otherwise, you don't get DC voltage. That's why in DC machines, armature winding we place on rotor, and field winding we place on stator, opposite to synchronous. Okay. Next, the most important in the complete construction is armature winding. It will take some time. So armature winding will take minimum 2 to 3 years. Right. Sixth one, armature winding. Armature winding. So if you get any question in gate examination from construction, more chance to get from armature winding only. See, armature means conductor. In machines language, according to Faraday's law, two things we require. What is that? Conductor and flux. Now that conductor we call armature here. Conductor means winding. That winding we call armature in generators. And flux is created by another winding. Which winding? Field winding. That's why armature and field we call. Why lamination of core? So just now I said no. Why lamination we are using? There is eddy current here because it is cutting. Whenever the rotor rotates, it cuts the flux lines. EMF induced current circulate, causes eddy current. That is eddy current loss. To reduce that only we are laminating. Okay. How low reluctance? So that is also clearly said. I don't know whether signals are how with respect to your point of view. If you remove armature core, remove the armature core totally. Now what is there between north and south? See, this is north pole. This is south pole. No armature here, no rotor. Then how flux will pass? North to south through air gap or not? Now air gap will offer high reluctance or low reluctance? High reluctance. Now the same gap let us fill with a rotor. Now reluctance will reduce or not? Yes. How reduce? Armature core, silicon steel, low reluctance path, like that. What is field poles? Yes, in DC machine, field winding is present in pole core. Pole core, not only DC, synchronous also field winding is present on pole core. Field poles means this is only field poles. This north and south are what? Field poles only. These poles are field poles. How the poles are created? By giving excitation to the field winding, poles will produce. Flux is passing. If there is no field current, no flux, no poles. Okay. Okay, right. See. Armature winding. So before going to the lap and wave connection, so armature winding in DC machine is what? Mainly two types: lap winding and wave winding. These two windings we use in DC. But in AC machines like induction, synchronous, what is the winding we are using? Two windings: short pitch winding, distributed winding. But in DC we use lap winding and wave winding. Okay. So before going to that lap and wave winding, lap and wave winding, first we go to some important terms related to this winding so that you can understand easily. Right, first, some important definitions I will give, some important definitions, like first, conductor, because this terminology you should know to understand questions also. First, we will see conductor. What is conductor definition here? If you remember simple loop generator, let it is North Pole, South Pole, and here we have A, B, C, D, two conductors. This is one turn it is. Even one turn, it is two conductors we consider. A, B, one conductor, C, D, another conductor. A, B is called one conductor, C, D is called another conductor. But from this end to this end, the wire is same or not? Same only. Then why we call completely it is a conductor? Yes, the conductor definition in machines here is the length of the wire which cuts the flux. See, whenever it is rotating, north to south flux is passing from this end to this end. Now, whenever it is rotating, see, assume that loop is rotating here. This turn is rotating. Whenever it is rotating, only this length of the wire cuts the flux. And this overhang will not cut. If you see actual machine diagram also, rotor is like this. Like North Pole, South Pole. This is AB, CD. Okay, AB, this length is AB, this length is CD. So only this length is cutting the flux, because whenever it is rotating, north to south flux lines are there from this end to this end. Whenever rotor is rotating, only this length will cut, and overhang will not cut any flux line. So the length of the wire which cuts the flux, we call conductor here. Okay, write that. The active length of wire, the active length of wire which cuts the flux, is called conductor. This is indicated with letter Z. Conductors we denote with letter Z. Next, turn. Next definition is turn. This is we indicate with letter T. Turns. Turn is indicated with T. Now tell what is a turn. This is a turn or not? Yes. AB, CD with overhang. This is a completely one turn. So what is turn definition? Two conductors. AB one conductor, CD another conductor. Two conductors with overhang is called a turn. Or two conductors will make one turn. Two conductors will make one turn. Okay, write the definition. Two conductors with an overhang is called a turn. Is called a turn. Two conductors with an overhang is called a turn. Now, what is the relation between turns and conductors? Can I write turns equal to Z by 2? Number of turns is half of the conductors. Two conductors will make one turn. If there are 10 conductors, means how many turns are there? 5 turns are there, half of that. Okay, remember this. Next one. Coil. This coil we indicate with C. What is a coil? Observe this figure. This is one turn. If you want a coil, let us make another turn in this. Now this is a turn or not? Yes. 2 turns is a coil. 10 turns also a coil. 100 turns also a coil. So coil may have any number of turns, but greater than or equal to 2. That's it. Any number of turns. So a group of turns. or a bunch of turns is called a coil. It may have any number of turns. Okay, and each coil has how many sides? Two sides. Each coil has two sides. This is coil side 1, this is coil side 2. Each coil has two sides. Okay, right here coil. A group of turns or bunch of turns. Bunch of turns is called a coil. Is called a coil. Each coil is having two sides. Each coil is having two sides. Each coil is having two sides. Okay. Each coil is having two sides. Next. So coil span, you know what is the coil span means? Coil span is what? The distance between the two sides of a coil we call coil span. Let it is beta. Coil span is the distance between two sides of a coil. Coil span it is. Next. Right side heading, single layer winding. Single layer winding. Single layer winding. So single layer, double layer, but practically which one we use? Double layer windings only we use. Whether it is DC machine or synchronous machine, double layer windings only we use. Let's see what is single layer winding first. Consider some number of slots in a rotor. There are some slots in rotor, for example, some slots. Now in that slots, we place coil sides. One slot, in one slot we place one coil side. Suppose there are two coil sides here, 1, 2. In this coil, two sides we have. Now, one coil side, that is coil side 1 I will place here, and coil side 2 I will place in some other slot. Some other slot, let us place here. This is coil side 2. Now, this is nothing but a coil. Coil is placed such that one coil side is in one slot, other coil side is in other slot, and like that any number of coils. So, single layer winding definition is, in this winding, each slot is filled by one coil side. Each slot is filled by one coil side only. That is called single layer winding. One slot, one side. Two slots, two sides. 10 slots, 10 sides. Okay, right here. In this winding, in this winding, each slot is filled by one coil side. One coil side. Therefore, how many coils are there now? Tell me. Half of the slots are not. Number of coils equals to half of the slots. Okay, half. Suppose there are 10 slots, means how many coils will be there in that? Half of that only, no? Because two slots is making one coil. This is one coil. Two slots is making one coil. Then if there are 10 slots, how many coils you can place? Half of that, that is 5. See, in any question, if you see single layer winding, number of coils equal to what? Half of the slots, that's it. Okay, you have to use this equation. If it is given single layer winding, number of coils equal to half of the slots. Next, double layer winding. Double layer winding. Double layer winding. See, in double layer winding, let us consider again some slots here. Consider slots and so on. Now in double layer, each slot is having even number of coil sides. Now we will place in each slot even number. Suppose I will take two sides first. Coil side 1, coil side 2. Like that, you can place even number. Two sides you can place, or 4 you can place, or 6 6 also you can place. Suppose 4, if you take 1, 3, 2, 4. 4 sides in one slot. 6 coil sides also you can place. 1, 3, 5, 2, 4, 6. But you should arrange all the coil sides such that two layers. This is called top layer and this is called bottom layer. Top layer, bottom layer. And according to our Indian standards, the top layer we always consider with odd numberings, odd numbers. top layer we always assign with odd numbers, and bottom layer coil sides we give even numbers. Even. Top coil side odd numbering, bottom coil side even numbering. Okay, this is our standard. One standard we follow. That's why if you buy a motor anywhere throughout India, the service of that motor anywhere everyone can do that, because same model everyone will do the windings. Same model. Suppose you bought your motor, maybe three-phase induction motor or anything, just damaged. Winding is damaged due to some sudden high voltage, winding burned. Now, if you go to rewinding, everyone will do the same procedure. That is, top is with odd numbers, bottom is with even numbers. Like that, they will remember that coil sets. Okay. This is also double layer. This is also double layer. This is also double layer. So simply in double layer winding, each slot is filled by even number of coil sets. Maybe 2 sides or 4 sides or 6 sides. But you should arrange that in 2 layers. Then it is called double layer winding. But out of this, which is the most common practical winding we use? This one. 2 sides only we use, not more than that. We will use only 2 sides in one slot, 2 coil sides in one slot. Okay, just remember definition. You will see the figures again later. Right. In this winding, each slot is filled by even number of coil sides. Even number of coil sides arranged in 2 layers. Arranged in 2 layers. Arranged in 2 layers. Like this. Top layer, bottom layer. Now, if we take first one, how many coils are there here? Tell me. Number of coils equals to number of slots or not? Because 2 coil sides in one slot. 2 coil sides, nothing but one coil only, that is. Okay. One coil has 2 sides. 2 sides, nothing but one coil. Anyhow. So number of coils in double layer winding is always equal to number of slots. Suppose they don't mention anything, they given only double layer winding. Then which slot you have to consider? This one. That is 2 coil sides in one slot. 4, 6, 8 and so on, we don't use practically. Just definition we are defining like this. 2 coil sides, 4 coil sides or 6 coil sides and so on. Practically we don't use all this. What is a practical case means? Only 2 coil sides. Okay, so whenever you see the word double layer winding in any question, take number of coils equal to number of slots. That's it. Okay. So this is some brief introduction of armature winding terms. Now we will go to the actual winding in DC machine is lap and wave winding. Let's see that. Right. Lap and wave winding. So as difference at the same time. Lap winding, wave winding, right? Side by side. Lap winding and wave winding. See, how can we say the winding is lap connected, or how can we say the winding is wave connected? So it is based on the appearance. Based on appearance of coils, we can say it is a lap connection or wave connection. Okay, first let us consider the figures. See, I'm taking a 4-pole or 2-pole. Let us take 2 poles and number of slots equal to 6. And single layer winding I'm considering in all. Single layer winding. Okay, now taking 2 poles. 2 poles. These are called developed diagrams or linear diagrams. These are developed diagrams. So I will show you again why we are drawing this type of figures in armature windings. In synchronous machines also we draw like this only. 2 poles, 6 slots, means under each pole how many slots will come? 3 slots. 1, 2, 3, 4, 5, 6. Total 6 slots. Then how many coils we can place? Tell me. How many coils? 3 coils, because single layer winding I given. Then how many coils? Half of the slots. Slots are 6. 6 by 2, 3. So number of coils are 3. 3 coils only we can place. So these are all slots. These lines indicate slots like this. So what is actually this is 2 pole 6 slots given. So if you see the actual machine diagram, it will be like this. 2 poles. Where is the poles located? Stator. The poles are located in stator. And slots is present in rotor. That is, this is a rotor. And in the rotor, we have slots. 6 slots total. 2, 3, 4, 5, 6. This is actual 2 pole 6 slots machine. But now the same machine I converted into developed diagrams we call, or linear representation of the same machine. 2 pole 6 slots. Now we will place winding in this coils. Let us place one coil side here and connect our other coil side is placed in other slot of south pole. This is one coil. Let us place another coil same as it is. First coil it is. Now second coil. Second coil is placed. Now place one more third coil. 3 coils only we can place here. Single layer winding. 3 coils are placed. Okay, this is third coil. Now if you want a lap connected winding, lap connection, how to make it is lap? Observe here. This is the end of first coil. Okay, and this is the starting of second coil. Now the end of one coil is connected to the starting of another coil under the same pole. The end of one coil is connected to starting of another coil under same pole. Now proceed as it is again. This is the second coil end. This is third coil starting. Now let us join these 2 points. The end of one coil is connected to starting of another coil under same pole. Now whatever the coils are there like that, join continuously. So finally you will get one end. This is armature terminals. This is our armature terminals. Now observe the coils once. How the coils looks like. The coils looks like overlapping one over other, just like plates. One over other we place. In the same way the coils are looks like. Lapping or overlaps. That's why this winding procedure we call lap winding procedure. Based on the appearance only we can say it is lap or wave. Now, why we are not taking this type of diagrams is, observe here. Suppose same as it is procedure you apply for this machine diagram directly. This is north pole, south pole. Place one coil side here and another coil side here. This is one coil. Place another coil here and another coil side here. Second coil it is, and third coil it is. After placing the 3 coils, connect as it is, end of one coil to starting of other coil. Then After connection, can you say what type of connection from this diagram? Is it lab connected or wave connected? You cannot identify from these diagrams. You cannot see that. Whether the coils are lap or wave, you cannot observe from this type of diagrams. That's why we are drawing this type of diagrams everywhere. Okay, clear all of you this point? Okay. That's why we take this type of diagrams always in the winding representation. Similarly, let us consider wave winding. But one important in wave winding is the minimum poles required for wave winding is 4. Otherwise, wave winding will not come. Minimum poles required for wave winding is 4 poles. And slots you can take any number. For example, let us take 8 slots. 8 slots or 10 slots or 12 slots, whatever it is. So you take 8 slots, for example. Now, there are 4 poles. Let North Pole, South Pole, North, South, South. Now, total how many slots are there? 8. Then how many slots per pole? 2 slots. 1, 2, 3, 4, 5, 6, 7, 8. 8 slots total. Okay. Now, how many coils you can place? Tell me that point first. How many coils you can place? Single layer winding only. Single layer. So, number of coils equal to half of the slots. Not more than that. Number of coils is half of the slots you can place. That is, if slots are 8, you can place 4 coils. 4 coils, half of that. See here. Let this is one coil. This is one coil, and second coil you can place here, and this is another coil. Okay, and here one more coil. So I'm not drawing 4 coils. I'm showing only 2 coils. See, this is one coil. Another coil is here, and the third coil, and fourth coil will be here. But I'm not drawing 4. Only 2 I'm drawing because I want to show a proper wave without any confusion. That's why only 2 I take it in this. Only 2. So if you want wave connection, the end of one coil is connected to starting of another coil. This is end of one coil. This is starting of another coil. Let third coil that is. The end of one coil is connected to starting of another coil under adjacent pole. Adjacent, not same pole. If you make it is under same pole, you will get lap winding, but wave will not come. Then I said minimum 4 poles required. Suppose you take 2 poles. You take 2 poles. Now the end of this coil, you have to connect to another coil. Where it is another coil? Under same pole. There is no other chance. Then you will get a lap connection here. With 2 poles, only lap connection is possible, but not wave connection. Now why we call it is wave? See here. After joining like this, end of one coil is connected to starting of another coil under adjacent pole. Then the coils looks like a wave here. The coils looks like a wave. That's why we call it is wave winding. Clear? Why we call it is wave winding? So definition is important here. In order to get wave, how to connect? In order to get lap, how to connect? Okay, first take the figures, so then we write the point. Take the figures first. So write the definition for lap winding. The end of one coil is connected to the end of one coil is connected to starting of another coil, starting of another coil, under same pole, then the coils looks like lapping. After connection, the coils looks like overlaps. That's why we named it is lap winding based on the appearance of the coils. Similarly, in wave, the end of one coil is connected to starting of another coil, under adjacent pole, adjacent, not same pole. If it is same pole, lap connection. If it is under adjacent pole, then it is wave connection, because the coils looks like a wave now. That's why we call it is a wave winding or wave connection. Okay. Now there are some important differences between these two windings. From here only we get the questions. See this lap and wave winding, this topic is very, very important. So in the future, in the next coming classes, we will see some topics like armature reaction or any other. In future, any topic, everything related to these windings only. If you don't have any idea of winding, you cannot understand some topics in future. These are interlinked now. So what are that points is? So one by one we will write now in the differences. So you should remember this point up to total completion of DC machines. Okay, that much important. See next, right? Next point. So this is regarding parallel paths. Number of parallel paths. Parallel paths in case of lap connection. Parallel paths we indicate with letter capital A, and this is equal to number of poles. The number of parallel paths in lap connection is equal to number of poles. Parallel path means it is with respect to current or voltage. Tell me. In parallel, voltage is same, no change in the voltage. Parallel path, any number of parallel paths, voltage remains same. But what will change here? Current will divide. If there are 4 parallel paths, current will divide into 4 parallel paths. Current divides into 4 ways. Like that, current division it is. Now itself, I cannot show parallel paths to you directly. But after completion of total armature winding topics, at the last, I will give the complete armature winding diagram with one example. There I will show you what is parallel path, how it is coming inside the armature. Okay. Up to that, you just remember this point. Right now, I cannot show, because every point from now depends on this point only. After this, whatever the differences we are seeing completely depends on this point only. Okay. That's why remember only this point. How the parallel paths we are getting, I will show you at the last of this armature winding topic. Okay. Right. Number of parallel paths in lap connection equal to number of poles. But in wave connection, the number of parallel paths is always A equals to 2. The number of parallel paths is always 2 in wave winding. Remember this. It is always 2 only in wave winding. Next, make a note below this. See, sometimes in the questions, objective type or numerical type, you may get some questions like simplex lap winding or duplex lap winding or triplex, like this. So if they said simplex lap winding, then A equal to P only. And if it is wave winding, A equal to 2. Simplex wave winding, A equal to 2. Wave winding. Lap winding, A equal to P. If they say duplex, then A equal to 2P. If it is wave winding, A equal to 2 into 2. If it is triplex winding, A equal to 3p. Lap winding it is. And if it is wave winding, A equal to 2 into 3. Like that, if it is a quadruple or and so on, they say multiplex. If it is multiplex winding, A equal to m into p. And if it is wave winding, A equal to 2m. Okay, remember this formula. Whatever they given, use this. But if nothing is given in the questions, just given lap winding or wave winding, then consider only this. Okay, and this multiplex or simplex, duplex, triplex, multiplex, this plex of the winding depends on commutator pitch. We have one term, commutator pitch. See, later I will show you about this, what is commutator pitch and all. Commutator pitch, this plex depends on commutator pitch. If commutator pitch is changing, your plex will change. That's it. So how it is, I will show you in the next coming topics. Just note down it is. Okay. In wave winding, there are 4 coils. I said already, I'm not drawing, that is, there are 4 coils here. There are 4 coils, but I'm not drawing all 4 coils. This is 4 coils. Okay. 1, 2, 3, 4. But I'm not drawing. Why I did not draw? I want to show only one wave properly. That's why I taken only 2 coils there. Like this, we connect it. Okay. So just note this one about multiplex winding. Whenever they given, A values will change. Now, most common question in the windings in engineering services many times is lap winding is suitable for dash and wave winding is suitable for dash. Many times in some other competitive examinations also same questions. Lap winding is giving low voltage or high voltage or low current, high current. So to understand this directly, we cannot say no right now. So lap winding, I may give directly, but I don't give directly. First, I will take one example. One small numerical we will solve, and from the output of the numerical, we will write the points again. Okay, write one example. Write one example. Consider a four-pole DC generator. DC generator is having, consider a 4-pole DC generator is having 100 conductors with EMF per conductor is, with EMF per conductor is 10 volts and current rating of each conductor is, current rating of each conductor is 10 amperes. Some data I'm giving. If you made a lap connection, what is the voltage current you will get? And if you made using the same data wave connection, what is the voltage current you will get? That is the question. Okay, current rating of each conductor is 10 amperes. Find voltage, current and power rating. Power rating for first one lap connection and second wave connection. If it is lap connected, what is the voltage, current and power? If it is wave connected, what is the voltage, current and power? From the result, whatever we get, from there we will write the points again. Okay, just leave some page in your notes for some differences to be write, one complete full page. and then take this example. Okay, otherwise take the example and then you continue differences as it is. Your wish. Now first I am taking lap connection. First I will take lap connection. If the armature or coils are lap connected, then what is the voltage, current and power we get? First lap connected I am taking. So when it is lap connected, tell me how many parallel paths we get. If it is lap connected, how many parallel paths we get? Just now I given number of parallel paths equal to number of poles. That is 4 poles, no? It is 4 poles. So total 4 parallel paths means the complete armature winding will divide into 4 parallel paths. This is armature totally. Inside the armature winding will divide into 4 parallel paths. Armature winding is coils only. The coils will divide into 4 parallel paths. That is I am drawing here. Total how many conductors are there in armature? That is given. Total conductors are Z equal to 100. Total conductors 100. And EMF per conductor how much? 10 volts. Current rating of each conductor how much? 10 amperes. Current rating. Now when we lap connected, total 100 conductors are there in this. Then how many conductors will come in each parallel path? Tell me how many conductors will come? 25. Equally distributed it is. 25 conductors here, 25 conductors here, 25, 25. Total 100 conductors. Now each parallel path we are getting 25 conductors. Now tell me what is the voltage rating of each parallel path? Tell what is voltage rating of each parallel path? One conductor voltage is 10 volts. If there are 25 conductors in series, what is the voltage? Additive. Series means voltage is additive here. That's why 25 into 10, nothing but 250 volts. All parallel path same voltage, 250, 250, 250, 250. So any one parallel path is enough. No need to find for all. That is itself voltage rating of this armature. Now what is the current rating of each parallel path? Tell me. Given that current rating of one conductor is 10 amperes. Current rating per conductor is 10 amperes. Then how many conductors are there in each parallel path? 25 conductors are there. Then what is the current rating? 10 amperes only. 10 amps only for each parallel path, 10 amps only. Why 10 ampere? One conductor current 10 amperes. How many conductors are there in series like that? 25 conductors are there in series. Then what is the current in series? Same current will flow in series. If you put 10 conductors, 10 amperes only, or if you connect 50 conductors in series, 10 amperes only, or if you connect all 100 conductors in series, 10 amps only the answer. Okay, so 10, 10, this is also 10. Now what is the total output armature current? Therefore, the armature current is 10 plus 10 plus 10, total 40 amperes. This is the rated current of armature. 40 amps is the current. Voltage rating is 250, current rating is 40. Now what is the power rating? Tell me. Power, product of voltage and current. 250 into 40. What is the power rating? 10 kilowatts will come. The power rating is 10 kilowatts. Okay, this is for lap connection. So same as it is, calculate for wave connection. Same as it is, calculate for wave connection. Check what you will get. Next, wave connection. If the same armature is wave connected, wave connection is used. Wave connection. Then how many parallel paths will be there in wave connection? Only 2 parallel paths. In wave connection, there is only 2 parallel paths. Number of parallel paths equals to 2. So total winding will divide into 2 parallel paths only. Any number of conductors or turns or coils, anything that is. Divide into 2 parallel paths. Okay, like this. Now how many conductors will come in each parallel path? Total 100. Total conductors 100. How many will come in each parallel path? 50. 50 conductors here, 50 conductors here. Now tell what is the voltage rating of each parallel path. What is the voltage rating? Voltage rating of each parallel path is 500 volts or not? Yes. 50 conductors in series. One conductor voltage 10 volts. 50 conductors in series means 500 volts. Now current rating of each parallel path, how much? What is the current rating of each parallel path? One conductor 10, 25 conductors 10, 50 also 10 amperes only. 10, 10. Now what is the output current? 10 plus 10. The armature current is 20 amperes. The armature current is 20 amperes. Therefore, what is the power rating? V into I. Power voltage is 500, current is 20. What is the total? 10 kilowatts. Okay. Now what is your observation from this? Whether it is lab connected or wave connected, power rating same or not? See, using the same winding, you made lab connection or you made wave connection, anything, your power rating will not change. Power rating remains same. But observe the voltage and current ratings here. In wave winding, you got high voltage, but you got low current. But in lap winding, you got low voltage and you got high current in lap winding. So lap winding will give high current at low voltage, and wave windings will give high voltage at low current. But power rating is remains same. Okay, so make a note below this. Note. For the same armature winding, whether it is lap connected or wave connected, the power rating remains constant. The power rating remains constant. Okay, but voltage and currents will change. If you know this point, there is one previous gate question. Directly you can answer that question without solving also. Just by observing options, you can put the answer. If you know this point, whether it is lab connected or wave connected, power will never change. Power remains same only. But voltages and currents are different. Okay, so write one point differences right now in the lap winding and wave winding. Write one point. It is suitable for low voltage, high current. Okay, wave winding will give high voltage at low current. It is suitable for high voltage, low current. Okay, high voltage, low current. Next point. Tell me, how many conductors are there in each parallel path? How many conductors are there in each parallel path? Observe here. Lap connection or wave connection. If total conductors are Z, how many conductors are there in each parallel path? Z by A or not? Number of conductors in each parallel path. Z by A. Check here. Z is 100, A is 4. 100 by 4, how much? 25. Now in wave winding also, how many conductors are there in each parallel path? Z by A only. 100 by 2, 50 conductors. Okay, so in general, number of conductors. See, these points important. Number of conductors in each parallel path. in each parallel path is Z by A. Remember this, Z by A number of conductors. Wave winding also same, number of conductors in each parallel path. In each parallel path is Z by A only, but if it is wave, you can write directly Z by 2 because A is 2 always in this. It never change. Next, in the same way, what is the current in each parallel path? The current in each parallel path is dash. Current in each parallel path is how much? Observe the figures. If total current is IA, what is the current in each parallel path? IA by A or not? If total current is IA, what is the current in each parallel path? IA by A. That is, if IA is 40, what is the current in each parallel path? 10 ampere, means 40 by 4. 40 by 4. 4 is nothing but parallel paths. Okay. Current in each parallel path, current in one conductor. Both points are same. See, try to remember this point. In armature reaction, we utilize this point again. Current in one parallel path, nothing but current in one conductor. Both are same only. 10 amps only, no both. Okay, remember this. The current in each parallel path is IA by A. Similarly, in wave winding, the current in each parallel path. Current in each parallel path is IA by A only. IA by A. Okay. Next point. Now observe the two figures in your notes. Tell the armature resistance is low in case of lap winding or wave winding. Armature resistance. See, this is total armature. The equivalent of this parallel path will give armature resistance. Now, what is the armature resistance for lap connection and wave connection? So, where armature resistance is less. So, already you know in networks, if there are more parallel paths, what is the equivalent resistance of that? Very less. If parallel paths increase, the equivalent resistance decrease. Yes, right. So, write that point. Lap winding, the armature resistance is low. The armature resistance is low because more parallel paths here. But in wave winding, the armature resistance is high value because only two parallel paths. The armature resistance is high. Okay. Next point. Number of brushes. Remember this point. Number of brushes equals to number of poles. Just like parallel paths, A equal to P. Brushes also number of poles. But number of brushes in wave winding is always 2. Number of brushes in wave winding is 2. Okay. So remember, up to this, still there are 2 more points we need to discuss. It will take time. So next class we continue this. So remember up to here. So still there are some difference. 2 points are there. Still 2 more points. So that will take some time. So in next class we continue this. So I think mostly tomorrow we don't have class, and Sunday we have full day. That is 2 to 8:30. Efficiency means we cannot decide directly because It depends on power rating is same now almost. Whether it is lab connected or wave connected, power rating remains same. That's why efficiency is almost same, but voltage currents little different, and there are some disadvantages of wave winding. So in the next coming differences, you will understand that. Okay.
So,
Hello.
let's explain single layer winding and double layer winding.
Single layer.
Double layer winding.
The single layer winding means in each slot we place one coil side only. Like that, how many coils you can place? Half of the slots. Means number of coils is less or not.
Yes, sir. Sir,
Then if coils are less, automatically
sir
turns are less.
we can give so many turns in that same slot.
You can give, but one slot, one coil side means how many turns you can place? Can you place whatever the possible?
Only one side.
One side only, one slot. Because of that less number of turns. Maybe you are thinking that in one coil side only I will place more number of turns.
Oh, yes, sir. Not like
So in next class you will understand that.
okay, okay.
So good evening, sir.
Tell me.
Sir, I don't get that the flux distribution in yoke, sir. Could you explain this? Like
Flux
5/2
distribution.
is
Page
the
number?
yoke, sir. I think it's 28 something.
This one?
No, sir, the yoke.
Yoke.
Yes, sir.
This one?
Yes, sir. Yes, sir.
Oh, what is here?
No, sir. How it is 5/2?
Because
if we keep like
if
more
total
number of
flux
poles,
total flux is 5 now suppose, then from here half of the flux will go in this direction and another half of the flux will go in another direction. No,
yes, sir. For 2 poles it is fine, sir. But what if we keep like 4
for
or
4 pole also same thing. Suppose you take 4 pole case. For example, there are 4 poles: north pole, south pole, north pole, south pole, north, south, north, south. Now how flux distribution? North to south only flux always flows. North to south, north to south, north to south. Now this total flux is let 5.
Okay.
Now in that half of the flux is going here and half of the flux
Yes,
going
sir.
here. Now again the same flux will come back. No, what is the flux here? 5/2 only. Again this is a flux north to south externally, south to north, like this. This is also 5/2, and here also 5/2, here also 5/2. 5/2 only, no, in the core.
Sir, but it should be 5/4, right, sir?
No, 5/2 because the flux per pole is 5.
Okay, okay, sir.
Each pole outcome is 5.
Okay. And sir, one common thing is the yoke we are commonly calling it as stator, and the field poles and those field windings are together called it as stator core, right, sir?
No. Stator poles are field poles. Because yoke is separate, poles are separate. But why we taken poles in the diagram is there is some purpose. Poles we are connecting to the yoke only, no. Just to give that point, poles are considered. Okay.
Okay, sir. Yes, sir. So and then in 30 years, 30.
Hmm.
No, 31. Yes, sir. Sir, here could you explain the formation of eddy currents one more time?
Because whenever flux is coming out from the pole, it is fetching for low reluctance. Now, which one will offer low reluctance? Tooth.
Tooth, yes, sir.
Now, whenever rotor is rotating, tooth is not at one place. It is moving, no, moving. So when it is
Yes,
moving,
sir.
the flux line also oscillate here.
Yes, sir.
During that oscillation, some EMF will induce in the pole shoe.
Okay, sir. Sir, and then 44 years, sir. 1 minute, sir. Sir, in case of lap winding, you said that we should connect like the two turns from the same poles. I don't get what you mean by same poles. Under same poles.
Same pole means at north. Suppose you take north pole. We started at north, and again we are connecting starting at north. Again we are connecting starting at north. Under same pole we are doing every connection. But if you take wave winding, the end of one coil connected to another pole, another coil where it is not at same pole, some other pole. It is.
Okay, sir.
Okay, adjacent.
Yes, sir. And then last road, sir.
Yes.
Sir, for pole pitch, what if we use like 6 poles? Still, we get the same 180-degree electricity.
Where? Which one?
In case of pole pitch, sir.
Pole pitch. Pole pitch also any number of poles, same definition. Angle between two adjacent poles.
Yes, sir. But if we use like 6 poles, we get the angle between two poles around 60 degrees.
No. Electrically 180 only. That is always. See, maybe mechanically 60 degrees you get, but electrically we have to take it is as 180 degrees. Pole pitch is always 180 degrees. Okay, electrically pole pitch we defined. Okay.
Yes, sir. Thank you, sir.
Hello, sir.
Next, Anil.
No, sir. Yes, sir. In commutator, we said one point. Na? In between brushes and brush water, so there is one spring.
Yes.
What is the main purpose, sir?
So that spring is pushing the brush. No, suppose if there is no spring, for example, this is the let us consider this is brush holder connected to the stator, and here we have one brush. For example, assume that no spring. Now this is a commutator. Whenever it is rotating, there is a friction between commutator and brush. Now brush size will reduce or not?
Yes, sir.
Yes. Now brush size will reduce. Whenever brush size will reduce, assume that some gap arrived. Some gap is there. Now who will push the brush towards commutator surface?
Okay, sir. Okay, sir.
Okay.
Okay, sir.
Next.
Hello, sir.
Pratyush, tell me.
Sir, in 44F, sir. Sir, here each coil set can accommodate n number of conductors, no, sir?
Each coil sets n number of conductors.
Is there any limit, sir?
Limit means suppose the slot he is having less height, then whatever the height is there, up to that only you have to take.
Okay, sir.
Okay.
Sir, another one, sir. In case of lap winding, we are connecting the first coil second side to the second coil first side, no, sir?
Yes.
Sir, if we connect that first coil second side and again if we connect it to the same slot of first, for getting a turn in a same slot, we are connecting the same coil in same slot, no, sir?
That you will understand in the double layer winding. It is single layer winding, no, present.
Yes, sir. Yes, sir.
In double layer winding, I will draw in the last diagram.
Oh, okay, sir. Sir.
Next.
Hello, sir.
Tell Vaishnavi.
Sir, while discussing yoke, you said, no, sir, in alternator and DC machine, flux produced is constant. And while discussing field poles, you said the flux distribution is flat top. Means that is varying, no, sir. Flux is not constant, no, sir.
No. Again, ask again.
Sir, while discussing yoke, you said in alternator and in DC machine, flux produced is constant. And while discussing field poles, you said the flux shape is flat top or trapezoidal. Means flat top or trapezoidal means flux is varying, no, sir.
Not understand. Whatever it is, what is the shape of flux distribution? Flat top only, no?
Flat top means it is not constant, no, sir.
Constant means, okay, you are considering like magnitude of flux, it is coming in one direction only, no? So why we taken like this is, under north pole, we assume positive case. Under south pole, we take negativities. We are considering. But actually, with respect to linear representation, it is not machine representation. See, if you take a machine diagram, can you draw any shape here directly? Flux lines only we have to represent like this.
Yes,
like
yes, sir.
this is not shape of the flux. But shape of the flux, when it will come in the linear representation, only shape will come. Variation, magnitude of flux. But flux is DC only. Okay, don't confuse in this. That is different. Okay. Next, Pawan.
Hello, sir.
Tell Pawan.
Armature winding is which material you use, sir? Copper.
Armature winding.
Which
Copper
material?
only, copper only, and standard wires, standard conductor. Standard conductor we use. Thin wires. Okay.
That's it, sir.
Okay.
Hello, sir.
Yeah, tell me.
Sir, 30F slide.
Hmm.
Sir, I guess it's 31 or 29 somewhere. That pole shoe. This one, sir.
Hmm.
Sir, here the flux coming out of the pole shoe is constant, no, sir.
Flux is constant, but after coming out, it is fetching for low reluctance path, no, automatically.
Yes, sir. My doubt is that
Ah.
like the pulsation of flux is actually experienced by the rotor part, no, sir. Like with respect.
Rotor, yes, rotor part only. That effect will be there on the pole shoe also, no.
Okay. So eddy current would be induced in both places, rotor and.
Rotor also, because anyhow rotor we are laminating, no, already.
Okay, sir.
That's why we taken in the pole shoe must be laminated, but practically only pole shoe difficult
So we are laminating the entire
completely.
field.
But if any question, if you got, your answer must be pole shoe only.
Okay, sir. Sir, one more thing, sir. That we told that leakage flux is less for open slots. Can you please like explain that leakage flux concept, sir?
Already, did you listen in induction?
No, sir. New batches did not get.
Leakage means you will understand first what is leakage flux definition.
Not aware of that, sir.
Leakage flux is nothing but it is the flux which links with only one winding. That may be transformer or induction motor or any synchronous machine, anywhere. So what is our aim generally? Whatever the flux produced in the rotor, that should reach, for example, I will take alternator.
Okay.
This is stator and rotor. Now to the rotor we are giving excitation. Now poles will form north to south. Now south to north, internally south to north flux direction, externally north to south. Now whatever the flux produced in the rotor, that should reach stator body or not.
Yes, it should be.
Suppose some flux lines are rotating here itself. Now it is a leakage flux or not.
Oh, okay.
Okay.
Okay. Yes, sir.
Now with respect to slot, how it is defined is, see, suppose one conductor is there here. One conductor I placed in open slot. Now it is carrying a current. Now according to the right hand thumb rule, there is a flux around the conductor or not? Yes.
Sir. Yes.
But observe, this is a gap of 2 centimeter.
Okay.
Okay. And this open width is 2.5 centimeter.
Okay.
Or let us take not 2.5 for example. Let us take it is 1.9 centimeter is there. Okay.
Okay.
1.9 centimeter. Now which gap is less? 1.9 is less.
Yes.
Now whatever the flux is producing around the conductor, most of the flux lines will go up to stator. This is stator, this is rotor. It is going, but some flux lines will rotate here itself.
Okay.
Now this is leakage flux lines or not?
Yes. Sir.
Now the flux is linking with only one part, not both parts. If both is linked, that is useful flux. But now it is leakage flux. But it is leakage flux is less here. But if you take same case semi-open slot, now what happens here is same current carrying conductor I placed here. Now what is the semi-open means? This gap is very less. This gap is very less. No, slot width here.
Yes,
very
sir.
less. This is 2 centimeter. This is only 1 centimeter. This gap.
Okay.
Now most of the flux will rotate here itself because flux takes the low reluctance path. Now leakage is more or not?
Oh yes, sir. Yes, sir. Got it.
That's why.
Okay, sir. Thank you, sir.
Next.
Sir.
Hmm.
Sir,
Hello,
pole arc. What
Hmm.
can you tell it once again, sir? Pole arc from where it?
Pole arc means this is only. Or if you take pole shoe completely, this is pole arc. This is pole arc. Or pole shoe or pole arc, pole face, all are same.
Sir, pole arc by pole pitch. Also, curve का length check करते हैं sir. Pole arc का length by pole
Yes,
shoe
yes.
का length.
Pole shoe always, pole pitch always 180 degrees. Pole arc is how much? Let it is some 120 degrees. 120 by 180. Calibrated. That is the ratio of pole arc to pole pitch.
So angle लेते हैं sir. Okay.
Okay.
Sir, one more sir. Sir, the ring fire बोल के बोले ना sir. Fire कैसा catch sir?
Because there, whenever spark is coming, it will damage the insulation between each segment. No? Whenever insulation is damaging, two segments will short circuit with respect to brush position.
Okay.
Then all segments shorted means internal coils are shorted.
Yes.
That is called ring fire.
Sir, can you please open the last page, sir? The differences.
This one.
इसके बाद का सर लास्ट पेज में जो डिफरेंसेस लिखे हैं इसके बाद मैं नहीं लिखा था सर इसलिए
only this last.
Sir, number of brushes. Yeah, which. This one only, sir. Sir, number of brushes equal to number of poles. Sir, brushes can't connect करते हैं sir.
In the last
Where do
diagram,
we connect those
last figure, I will give all this. Okay. In the next class, last diagram, I will give.
Hello, sir.
Yes.
Thank you, sir.
Okay.
Hello, sir. Good evening.
Good evening.
Sir, sir, in the ring fire case, in practically, you said that in 2 or 3 months we are regularly changing that process. So, in practically, is it happening that some fluctuation of voltage will be happen so that we know that now it is time to change?
Yes, yes.
Some voltage fluctuation from the rating.
Brushes only you are talking.
Yes, sir.
Number of brushes?
Sir, I am talking about ring fire.
Okay, ring fire.
Means how we know that now the time is to change that brushes?
Simple. When you switch on motor, sometimes if suppose if there is no ring fire, brush is completely worn out or wear and tear, completely wear and tear. Then there is no contact between commutator segment and internal armature. Then motor will not work now first.
Okay.
Then you have to understand
some other. Okay. But some other commutator segment will be working. So that some voltage will be induced, but that will be from less than the rating.
Yes.
Then we will know that it is the time to change the brush. Some
so automatically the performance of motor will reduce now.
Yes. Because we have to change it for a complete burnout.
Yes.
Sir, another topic is that we are in case of synchronous or in case of DC, we are calculating that flux. That is flux is it is DC value, but when we are calculating it from B average means that B wave is sinusoidal, and we are calculating it is sinusoidal. How we are taking that full wave means its waveform is like full wave. From where we are calculating phi average.
Okay. But here in DC machine we don't calculate total B. I will give some questions there. You need to find the total
4 BP LRY to
Yes, yes. But here we don't use that. You will get some other type of questions like you need to find flux per pole. To find flux per pole is B into A, and B into area of the surface of the armature core will be pi dl, the formula of this. So there I will show you how to find that flux per pole.
But sir, that B wave is sinusoidal because it is specially displaced.
Here it is not required. Sinusoidal we don't displace, no, it is. What is the shape of flux distribution? Flat top in DC machine. Synchronous machine only we use that. Okay.
Okay.
Next, Avinash.
Hello, sir.
Tell Avinash.
Sir, you are told that brushes are connected to the commutator, but if the spring are fails to operate, then the brush is disconnect from the commutator.
Yes.
Then sir, it will be there open circuit success. Then how sparking will occur? Sir, at that
Suppose if brush is at the top position,
yes,
then automatically due to gravity, brush will be falling on the commutator surface only, no?
yes, sir. Sir.
And then there is a loose contact, no?
Okay, sir.
Okay.
Yes. And sir, the duplex winding and triplex winding you are told about that. Sir, please explain it once again.
So that duplex and triplex depends on commutator pitch. In the next class, I will show you what is commutator pitch. If commutator pitch changes, that is called duplex or triplex. How it is, I will show you in the diagram that is.
Okay. And sir, in induction motor, if we have used open slots, then what will happen?
If we use open slots, there is some reactance variation because leakage will change. Reactance of rotor will change. When reactance of rotor will change, it will affect the starting torque and maximum torque. Okay.
Yes, sir. Sir, that condition we can't face in DC machines and synchronous machine.
No. Because that no. That is working on induction, but it is not working on induction here.
Okay, sir.
Okay. So next class we meet. Good night.